Hello, everybody. Welcome to one more telecom seminar, which is hosted by the Technology Innovation Institute in Abu Dhabi. As many of you know, since March of this year, we are organizing a series of telecom seminars, which have been delivered by leading researchers and professors of our scientific community. And the seminars are being held on a bi-weekly basis, usually on Tuesdays, and all the previous seminars have been recorded and are available at the TII YouTube channel. But you can also see all the upcoming and these previous seminars at my homepage. And I will write later the link in the chat box. Well, for today, we are pleased to have Professor Fan Yang as the speaker of the seminar. So Professor Fan Yang is a professor at Electronic Engineering Department in Tsinghua University in China, and he's a fellow of AIDRC. He received the bachelor and the master degrees from Tsinghua University and the PhD degree from University of California at Los Angeles, United States. Professor Fan Yang research interests include antennas, surface electromagnetics, computational electromagnetics, and applied electromagnetic systems. He has published 6 books, 8 book chapters, and over 500 journal articles and conference papers. Professor Fan Yang served as an associate editor for IEEE Transactions on Antennas and Propagation, associate editor-in-chief for Applied Computational Electromagnetic Society journal, and he was deputy chair of 2014 IEEE Antennas and Propagation International Symposium. He's a co-founder of Beijing Antenna Corporation, which focuses on his hardware and system application. So, as you saw from his biography, Professor Fan Yang is a very active researcher in Reconfigurable Intelligent Surface in surface electromagnetics, having published many books and papers on this theme. And his today's talk will focus on that, especially in the RIS design and typical applications, the development of surface electromagnetics, and he also discussed some future directions and the intrinsic challenges. So Professor Fan Yang, thank you so much once again for accepting our invitation. Now the floor is yours.
Okay, thank you, Daniel. Thanks very much for your invitation. And also I would like to thank to our audience to spend some time to listen to this talk. My name is Fan Yang from Tsinghua University. And the talk today is the Reconfigurable Intelligent Surface. I would like to call it a pearl in the surface electromagnetics. So on this cover page, you see 2 pictures. On the left is, well, the surface electromagnetics locate. I will explain that in a few minutes. And on the right is a photo of a RIS surface operating at millimeter wave frequency band. And also I will show some measurement result of this surface in the communication system. So with that, let me move to the first slide. So nowadays, many researchers from different areas, electromagnetics, communications, and many others, they are interested in the reconfigurable intelligent surface. And here we like to just show how RIS operate in a communication environment. So we have base station, it can direct radiate to the users, or through the RIS, it's reflected to the users. So from this scenario, so what we see is it has been transferred from the conventional circuit processing. We only process the voltage and the current in the time domain. Now with the RIS, we are able to manipulate electrical and magnetic field in the space. So that means not only we do the time processing, we also do the space processing. So that will give us an abundance of freedom to enhance our system performance. So now we all familiar that reconfigurable intelligent surface originate from metamaterials and metasurface. But if we go further, a little bit back to the history, so we see a lot of surfaces from the Huygens principles to the frequency selective surfaces to reflect array antennas. We see there are a lot of surfaces that have been investigated to manipulate electrical and magnetic field in space. And with that, we would like to call it surface electromagnetics. So we have RIS and we have surface electromagnetics. So with that brief introduction, here's the outline. So first, so I will have a brief overview of the surface electromagnetics. So what do we mean by surface electromagnetics? And then the second part, so we will move to the design of this reconfigurable intelligent surface from the model analysis, from design consideration, from the measurement, from different views back. And after that, so we will see how we try to use this RIS in the real 5G application, and also some in the future 6G application. So this is outline. Now let's move to the first. So when we talk about electromagnetic surface, we can easily think of some very classical surface. As we see here, we may have a perfect conductor, a PEC surface, which will completely reflect the incident wave. And also we may have a surface between two medium with different constitutive relations, different epsilon and mu. And on this surface, we see the reflection, we see the transmission. And this surface, these classical surfaces, they are uniform along the surface. So that means along X and Y, the tangential direction, the surface is uniform. There are no variation in the space. Even for this very classical simple surface, so we see very interesting phenomena that follow the Snell's law of reflection and refraction. So we have some very interesting angles, like for the total reflection angle and the zero reflection angle, also known as Brewster angles. So a lot of interesting happens for the uniform surface. And then the next step, from uniform surface, we will go to the periodic surface. And one example for that is the frequency selective surface. Let me see, are there any questions? Oh, no. Okay. Sorry for the interruption. Frequency selective surface, which start from the about 1950-60, and we see some publication about 1970s. So this one, from my personal viewpoint, is a very big milestone. So we move from uniform to periodic. This is like when we deal with the circuit, we start with the DC circuit, and then we move to further to the alternative current circuit, so AC circuit. From DC to AC, that is in the time. And from uniform to periodic surface, that is in space. And then this frequency selective surface, it can operate as a space filter. So that means if we look at the amplitude versus frequency, within a certain frequency, the electromagnetic wave can go through. This we call it passband. And in other frequency, the electromagnetic wave will be reflected. It's a space filter for electromagnetic wave. And it has a lot of application. For example, this is a picture from Banani's book. This frequency selective surface is used to reflect the high frequency like X, Ku, and Ka, but it is transparent for the low frequency S-band. So it can incorporate two feed in a parabolic reflector system. So this is the FSS reflector. So this can have a field effect and change the amplitude. And later on, another about 20, 30 years ago, around year 2000, so people start to look at instead of amplitude, look at the phase information. So if we have very thin surface noded with this periodic square patch, and when we look at the reflection phase of the surface versus frequency, For conventional PEC, the reflection phase is 180 degrees. PMC is 0 degree, but PMC does not exist in nature. For this periodic surface, if we look at the phase, it is shown in this blue curve. At a certain frequency, the phase is close to 0 degree. So that resembles a perfect magnetic conductor, and that we call it artificial magnetic conductor. So this thin surface has a 0 degree phase behavior. And then furthermore, if we look at it in more recent years, we see some new progress. For example, this is a very well-known paper in the Science journal published in 2011. So light propagation with phase discontinuities, generalized laws of reflection and refraction. So by changing the surface geometries, instead of the reflection in the mirror direction, it can go to any anomalous direction, just because we use the phase discontinuity on the surface. And this is in optical region. In the microwave region, we also see many interesting design. For example, if we have this small element, and then if we rotate the direction, and we see the slot oriented along different direction, we can also have the capability to manipulate the direction of electromagnetic wave. And beside that, we can also change the size of each element from very small element to large element. And with this surface, it also has the capability to manipulate electromagnetic wave. So if we look at this surface, we would like to call it as quasi-periodic. Because if you look at the grid, center of this each element, they are at the same location, it is periodic. But if you look at the element of each individual unit cell, it is different. So that we would like to call it quasi-periodic. So now, if we move all this on the same slide, we look at the development of electromagnetic surface over the time. We compare that to the time domain circuits analysis. When we do the circuit and signal, we start with DC signal. And then later we move to the AC signal. And later, if we want to transfer our voice or images through the space wireless, so we use the modulated signals. They are all in the time. When we look at the surface in space, we see very similar trend. At the beginning, we look at the uniform surface, uniform in dielectric interface, or uniform PEC. And then this time, we can just by changing the curvature of the surface to do the focusing, for example. But this time, the surface is uniform. And then we move to the periodic in the space, this periodic surface. And it can work as a spatial filter, or it can change the phase of the reflected electromagnetic wave. Of course, it has many other properties. And then later on, we move to the spatial modulation. Instead of modulation in the time, now we do the modulation in the space. And then with that, we can design a reflect array with a planar surface, but it can still focus in the beam. So this is spatial modulation. So nowadays, people are trying to combine the time modulation and the space modulation on the same surface. So that is the interest nowadays, and it has a lot of applications. And one example is to use to build a large phase array antenna. So this shows the development of the surface. And then nowadays, if we look at the literatures, so we see many different electromagnetic surfaces. For example, if we focus on the magnitude response, or we try to manipulate the electromagnetic wave magnitude. So we have the FSS, as we discussed just now. In the optical region, the optical grating, and also planar absorber. So that's manipulate the magnitude. If we want to change the phase, we talk about artificial magnetic conductor, and there are some certain phase shifting surface. and also holographic surface. So that's based on the phase change. And beside the magnetic phase, and also we have the polarization. So we can have a surface function as a polarization grid, known as a polarizer, or it can use as polarization converter. Beside the plane wave, we can also manipulate the surface wave. So we see the surface known as a soft or hard surface, high impedance surface, EBG surface, and so on. So there are many, many surfaces focused on different applications or different ways to control electromagnetic wave. And nowadays, we see a more generalized term like Huygens surface or metasurface. So this is a more generalized term. And nowadays, we are more interested in on active functions. If we integrate some active functions into the surface, so we have the reconfigurable surface, programmable metasurface, or grid arrays. So we see so many different research has emerged in this area. So with all that, we would like to call the surface electromagnetics. A new area emerged into the community. And of course, one of the topics today is about reconfigurable surface, or RIS, which is a very brilliant pair in the surface electromagnetics. And then how does surface electromagnetic differentiate from other knowledge or other research directions? So here we just like to show a diagram in the space, how we categorize them with respect to the space coordinate. Traditional, when we look at the general electromagnetic theory, so we can analyze radiation and scattering from 3D object. So that means for an object, its dimension in the X, Y, and the Z, they are all comparable to the wavelengths. So we have to use generalized electromagnetic theory, and we have to solve Maxwell equations. So nowadays we have many software can do that, but still it's very time consuming. On the other side, instead of the three-dimensional, if we look at the circuit analysis, in the circuit area, so all the elements, the source, the resistors, the capacitors, the diode, the transistor, they are all small compared to wavelengths. So that means the space dimension, they are zero dimension. So we use the topological connection. So we consider how this circuit, the voltage and the current change with time. But in space, as we mentioned, it is a zero dimension because it is much, much smaller compared to the wavelengths. And then if the frequency increase, so we see now the element or the transmission line is comparable to the wavelengths. So at least we look at the transmission line. When we look at this, the voltage on the left-hand side may not be the same to the voltage and the current on the right-hand side. We see the transmission line effect. And here, so we said this kind of structure, it is one-dimensional. The length is comparable to the wavelengths, whereas the horizontal dimension may still be small compared to the wavelengths. And this is the foundation of the nowadays microwave circuit. But now if we look at this, we have zero-dimensional, one-dimensional, three-dimensional. Apparently, there's one area that has not been given fully attention, which is a two-dimensional. For the two-dimensional, it is a surface we discussed just now. In the horizontal dimension, Lx and Ly, they are comparable to wavelengths, but their thickness are much smaller than the wavelengths. So this is a 2D problem. And this is our interest. The surface electromagnetics try to deal with this surface EM phenomena, try to understand what's happening. Can we generate some new devices? How we implement them in practical system. So this is what I would like to call it surface electromagnetics. And nowadays we see to realize this functionality, surface electromagnetic has two prominent features. The first one is try to digitize the surface. Instead of a conventional continuous surface, now we have digitized the surface. And then that can provide a distributed, well-localized wave control. Based on the sampling principle in space, we discretize the surface into many, many unit cells, like an array of unit cells. And each cell can have individual control of electromagnetic wave. And then the surface distribution of this cell will generate an entire function to manipulate electromagnetic waves. And furthermore, for the unit cell, we would like to have the full control of the wave. That means we would like to have simultaneous control of the magnitude, phase, polarization. And more advanced, we would like to have anisotropic or even bi-anisotropic. We need to consider the visible, the oblique incidence effect, and the invisible, which is surface wave effect. We need to consider dispersion, bandwidth, nonlinear property, and also, as we discussed just now, the real-time control. So we integrate the surface with some circuit components. So that is the surface electromagnetic. So that will give us an abundance of capability to manipulate electromagnetic wave in the space. And nowadays, if we look at this research direction of the surface, now we see the uniform periodic, quasi-periodic, or time-space modulation. So that's what we have seen already. And if we look in the future, these surfaces are all linear surfaces. And there are a lot of things that happens that lead to have non-linear properties. So also we see nowadays in some literature, there's some non-linear surfaces for the second order harmonic generation and so on. And then this kind of surface, if we look from another viewpoint, they're all devices. And on the fundamental, we need to have some basic theory for this surface. This is like we have the Kirchhoff current and voltage laws for the circuit analysis. We have the telegraph equation for the microwave circuit analysis. And we also need to have some basic laws and equation to describe the surface behavior. So some basic model, some method, some principles. That's some both basics need to be developed. And above this device, we need to be able to build systems based on the surface. So this system can be for the communication, for the radar detection, for the imaging, or even for the parallel computing. So there's another thing that can be done based on this surface. So that have, as we would like to say, always it has great challenges, while it is grand opportunities for our researchers. So that is a brief overview of the surface electromagnetics. Now let's focus our point onto the reconfigurable intelligent surface. How do we really design an RIS? So as we mentioned earlier, so this is a surface that's with the spatial and the temporal modulation on the surface. And with that, with the spatial modulation, so we can focus the beam. With the temporal modulation, the beam can be scanned in the space. And of course, this surface can have many, many more functions. But now let's talk about the focus beam and the scan of the beam. So in order to focus and the scan of the beam, the key point is to do the phase tuning. So for example, if we have wave incident from a horn or from plane wave far away, it comes to the surface, and then through each element, it will be able to manipulate the phase by the element phi r, and then reflected, we have phi. So for the phase tuning, there are different approaches. we can have analog tuning, as we see on the left. By rotating the orientation of this element, we can do the analog tuning. We can have the phase continuously change from 0 to 360 degrees. So this we call analog tuning. And we can also do the digital tuning. So we can have a switch on and off. So we can have two different phase status. So compared to the analog tuning, the digital tuning is simple, the performance is more stable, and the cost is also lower. But when we use the digital tuning, the first question we have to answer is how many bits we want to use. Are we going to use one bit, or we use multiple bits to discretize the phasing? So to answer this, we have done some investigation. We do some comparison. So if we choose a surface consisting of 10 by 10 unit cell, 100 unit cell, then we show the radiation pattern from the surface. We see the black one is continuous surface, continuous phase. So we have this beam. And also we can change the phase, we can scan the beam to 30 degrees. And then if we do the discretization, 3-bit, we have almost the same performance as the continuous. 2-bit, so that's red one. So we have some high side lobe. And 1-bit, the side lobe is even higher. But nevertheless, we see that 1-bit can still generate the same beam width as a continuous. And also it can scan the beam into the direction of our desire. So that means even 1-bit is very, very simple, very, very basic, and very, very fundamental, but it can generate the correct beam width, and it can generate the correct beam direction. The price we pay is the side lobe. See, the side lobe is about minus 13 dB, whereas originally the side lobe is minus 25 dB. But this problem, although this problem can be alleviated if we move to a large array. So this is another example. We do it 40 by 40. So we see now the side lobe for the 1-bit case is below 20 degrees, below 20 dB. And also when scan to the 30 degree, it is also below. So that means if we have a large surface, the side lobe can still be controlled with a good acceptance. So this is about the radiation pattern. The next, so we move to the gain or the loss of the surface. So this will show it for the 10 by 10, the quantization loss due to the phase error. For the 3-bit, it is very small. It is about 0.2 dB. For 2-bit, it is also okay, about 0.5 to 1 dB. But for 1-bit, because the side lobe is higher, so the quantization loss is about 2 to 3 dB. Okay. And then this shows the efficiency. So original reflected ray continues, so we can have an efficiency, aperture efficiency about 75%. But we use a discretized phase, so the efficiency will be lower. So this is for 10 by 10. And a similar thing, we can have 40 by 40. And now it is roughly like 3 dB loss for these 1-bit designs. So this answers the first question. So how many bits shall we choose? We choose 1-bit, 2-bit, or 3-bit. We have to find a balance between the system complexity and the system performance. 1-bit is simple, but the performance will degrade. 3-bit has good performance, but the complexity increase. So this is the first question, the quantization. So the second question, so if we can afford those performance degradation, but we would like to have simple and low cost, we move to the 1-bit design, 1-bit RIS design. And this just shows a very simple fundamental design. We have a patch antenna, and then we have a diode right here connected to the ground. So if it's off, so we have this one. This is a 1-0 mode. We have without the wheels, so we have this red dashed curve. We have the resonance frequency about 13.5 gigahertz. And then when we short it to the ground, so we see this. So it has either a half mode, which operates at a very low frequency, 5.3 gigahertz right here. Or it can have a 1.5 mode, so it has a relative high frequency, 16.2. So we have this resonance, when the wheel or the diode is on. So now if we look at the phase difference, so we have the phase difference like this. And this, we have 180 degrees between on and off. And here we also have another region, we have on and off. But usually we don't use the first resonance because it is too sharp. The bandwidth is too narrow right here. So we'd rather to use here. So this is how we can use the on and the off of the pin diode to operate at the different mode and at certain frequency, so we can realize 180 degrees phase difference between the two status. We can realize 180 degree 1-bit phase tuning. And then in practical, we have to consider the effect of the pin diode on. It is modeled as a resistor with a series inductance. Off, it is a model with a capacitor series connected with an inductance. And this is the actual design. We have the pin diode right here. And then we also need to have a biasing line and the fan-shaped branch to isolate the RF and DC. And then with all this, we look at the position where we put the biasing. Usually we put it right here. Well, we see the electrical field is minimum. Okay, with that design of the element, we look at the performance of this element. So usually we have a relatively good reflection. So the loss is about less than 5.5 dB. And then when we look at the phase, we see the phase right here and the phase right here and on and off. When we look at phase difference, at our design frequency, 14.25 gigahertz, we get a phase difference of 180 degrees. So that is the 1-bit design. And also, we minimize the biasing effect. We see on and off with biasing or without bias has very similar performance. So that's about element design. So next, we try to build an array consisting of this element. So we see we build a 10 by 10 array, and this is the element, this is a pin diode, this is a biasing line, and on the back, we see the fan shape, and we see all the DC line. And the microcontroller unit control all this, and then we use a horn to illuminate on this surface. And this is the result about the focusing and scanning of the pattern. So we can have 0-degree beam, or we can have the beam scanning from about -40 to +40. So this is a scanning result. And we look at the gain over the scanning from -50 to 0 to 50. And also we look at the broadside beam versus the gain versus frequency. So the horizontal axis now is frequency. So we see the scanning of the gain. So this is about 1-bit designs. So from the element design to the array performance. And based on that, we see a lot of new progress. For example, the first thing we see is from 1-bit to 2-bit, from 1-bit to 2-bit. So that is a balance between the complexity and performance. So we design a 2-bit reflector array at S-band, and we use a polarization conversion plus resonant lens approach. So the insertion loss is about 1.1 dB, and the fourth status is like this. So this one, we change from horizontal polarization to vertical polarization, and we control the lens. So this is a longer lens, this is shorter lens. So we can change the reflection phase. And then we're using the mirror method. So from the right to bottom, now from the left to bottom. So we can have some opposite status, and that will give us 180 degrees phase difference. So now these four status can give 0, 90, 180, and 270. So that's a 2-bit phase resolution. And based on that, we build the prototype. And then we measure the scanning performance and we measure the gain over the frequency. So now with this 16 by 16 element, so we have a gain more than 22 dB. So that's, we change from 1 bit to 2 bit. And also we see some progress we do from reflection type to the transmission type. So this is a simple design. We have 2 layers, and then we have slot on the first layer, slot on the second layer, and for each layer we have a pin diode here, and we have a pin diode here. So we need at a minimum 2 diodes to realize 180 degree and 0 degree phase. And then this is our simulation result. We do have this 180 degrees. And then we build a prototype. This is again another 16 by 16 element. And then we put the array, the feed, and the probe. And then we have a control board and a power supply. This is a focusing beam at both sides, and this is scan beam of this surface. So this from the reflection to the transmission. Okay, and then we can also use this one to build very large scale panel, because we already mentioned it is very simple, low cost, and no power consumption. And this is a design that we use 40 panels. Each panel is 16 by 16, 256 elements. So the 40 panels in total is 10,240 elements with a size of 2.5 meter by 1 meter, and realize a gain with 37 dBi. So this one we use FPGA parallels control, so we can switch the beam very fast in the scale of microsecond. So this shows the pattern of this structure. Since we have very, very large array, so we see the beam is very, very narrow. The hard power beam is about 0.7 degree in the broad side and 1.56 degrees in 6 degrees. So we scan from 0 all the way to 60, 70, and 80. Furthermore, instead of focusing beam, we can also realize a null in the middle. As we see in the center, we have very sharp null in the middle. So that is realized by changing the phase distribution over the surface. Okay, so this is the large panel. Another design. So this kind of surface is capable to be scaled to very high frequency. For example, the terahertz RIS. So this in the terahertz, so we have to use some integrated circuit design. This is more like a chip, but compared to the conventional digital IC, analog IC, and RF radio frequency IC. Now we have to do some IC with an electromagnetic performance. We call it EM IC or EM chip. So this is just show the chip. So we use the similar process as we design IC. So this is a 16 by 16 element terahertz RIS. And if you look into the details, so this is a small section, 3 by 3. So this, if we look at one of them, so we have a dipole element, and then in the middle, we integrate a HAMP device. By turning this HAMP on and off, so we can have different reflection phase from this dipole element. And with that, we also done measurement. So as we see, we have a horn antenna. This is a transmitting, receiving, and this is the terahertz RIS and the test. And then we have a control board here. Very interesting, our control board is much, much larger than our surface right here. Then we have the DC power supply. And then this is a measurement. The magnitude and the phase, as we see here, we can have 180 degree phase difference between the on and the off status. And also use that one, we can also measure the scanning performance from broadside to about 10, from broadside to 10 degrees and 20 degrees and so on. So this, we can scan it from the conventional microwave frequency to millimeter wave frequency, and finally to a terahertz RIS design. Okay, so now we talk about some designs, some consideration of the RIS. The next, we're trying to see how we can implement the RIS in the practical applications. So if we look from the development from 1G to 6G, from the perspective of antennas, from 1G to 3G, we see usually we have single antenna in the base station. So either we have omnidirection pattern or we have sectoral pattern. So we cover from 0 to 120 degrees, but it only have a single antenna. And then to the 4G, people try to implement the MIMO technology. So now in the base station, we can have 4 to 16 antennas in the base station using the spatial resolution. And now in the 5G applications, people are trying to use massive MIMO, try to further utilize the freedom in space. Now the antennas in the base station goes from like 4 to 16 to 64, 192, or even 256. What happened in the future 6G? In my personal viewpoint, the antenna size need to be further increased. For example, it needs to go from 100 to 1,000 of elements. So that cannot be realized with conventional technology. But RIS is a good approach to incorporate 1,000 or even more element into the base station. And furthermore, it can be implemented not only in the base station, it can also be implemented in the propagation environment, also known as a smart environment. So RIS have a lot of potential in the upcoming 5G and 6G communications. And this just shows nowadays various RIS design that our group have developed over the years. As we discussed, we can go from reflection to the transmission. We can go from single polarization to dual polarization, from 1 bit to 2 bit, to improve the bandwidth, for example, over 50%, to enlarge the scan angle above 60 degrees, to enhance the size of the panel to over 10,000 elements. These are all possible. And furthermore, instead of the semiconductor, we can use mechanical tuning. Instead of pin diode, we can use varactors for the tuning. And also we can incorporate some amplifier into the element design to realize active functions. And also we already just show some terahertz designs. And this is another design to have simultaneous reflection and transmission. And this is a more recent design to have multiple beam over the same surfaces. So there's a lot of things happening in the RIS designs. And to make it commercial, and also we founded a company in 2018, and we have different RIS product. This, for example, the 3.5 gigahertz 2-bit, 4.8 gigahertz 2-bit, 5.8 gigahertz, 26 gigahertz dual polarization, 28 gigahertz, and so on. And after build all this RIS product, so we are always asked, so where should we use these products? Where are the real actual application? And also we did some effort. For example, we use this RIS surface to build a phase array. We call it RIS phase array. So it has different frequency, and it is usually 256 elements with a gain about 20 dBi, 2D scan, and switching time is less than 2 microseconds. So this one can be used as an effective extension and supplementary coverage of the 5G communication. So compared to the base station that's used nowadays, It has no cost and no power consumption. And the construction and operation investment is also significantly reduced. So with this product, we have used it in the intelligent power grid. Because the power grid, many power grids, they are in the rural areas where the communication network is not covered. So if we want to cover that, use the nowadays 5G network. So it has a limited range. It needs large power and is relatively high cost. So this is not feasible. So we are trying to use our RIS-based communication system with a no cost, but realize a wide coverage. So this shows this is a target that we have, and this we install the RIS phase array to monitor the transmission signals or the situation within this target. And then we can transfer the high definition video back to the central control. So with that, it can help to improve this intelligent power grid, especially in the rural area. Another example that we also done is to realize the communication for the offshore or cross-sea communication. For example, in this situation, we have the ships go across this line and it's up to 50 kilometers. So the 5G communication network cannot cover in this range. And what we do is we install a RIS array right here, and we install very small terminals on the ship. So when we go through from this point to this point, 15 kilometers, so we can maintain good communication with the user on the board. Especially when we come close to 3 kilometers, the transmission rate is still higher than 50 megabytes per second. And over the entire region, it can be upper than 60 megabytes per second. And considering this is only use less than 1 volt transmission power. So it is very efficient for this offshore and cross-sea communications where the conventional 5G base station cannot cover. And for some other application, so this is another type of application to cover the blind zones. So this is another prototype. It consists of 48 by 48 element at millimeter wave frequency band. So if the base station and real user are blocked, for example, by a building or here by an absorber, we can put the surface right here. So it will be reflected by surface and then received by Hall antenna. So we test the signal intensity, reciprocity, and signal strength. We see a very satisfactory result. And then we move to the outdoor test. So the first test, we have base station, we have RIS surface, and we have the terminal. Right here, the distance is about 30 meters and 22 meters. And we see the enhancement about 12 dB. And the right one is a more practical situation. So the base station is located on the roof of the 11th floor. So this is our base station. And then this is our RIS. So the distance between these 2 points is about 120 meters. And then the user is on the other street. And then from user to here is about 50 meters. And in this case, we see the enhancement of signals about 5 dB. So that can help us to enhance. And this is another system. We use RIS both in the near field and far field. It's a hybrid system for millimeter wave communication platform. So for the system framework, the transmitter has a RIS, this one. The relay side has another RIS like this, and then the receiver. And then we operate at 28 gigahertz with a bandwidth of 800 megahertz with a rate about 1.68 gigabyte. Support 2 user switcher or the 2 users simultaneous 2 users. These are small videos.
The relay utilizes a RIS with 2,304 elements to reflect the signals from the base station to the user with the high array gain. At the user side, real-time data reception is accomplished by a neural network. Here we can see the received constellation, data rate, and the recovered 4K videos. This prototype can achieve a real-time data rate of 1.6 gigabytes per second.
Okay. So with that,
The relay utilizes a RIS.
So we also get some recognition of the RIS. And for example, the 2022 Geneva International Exhibition. And we believe there's a lot of things can be done with the RIS and some prospects of the RIS. So we have already verified we can use the RIS to cover the blind zone. And also nowadays we are doing some tests to use active RIS with power amplifier to enhance the signal strength. And also we can use to enlarge the base station signal range, for example, from less than 1 kilometer to up to 5 kilometers. So that can use in the remote areas, remote mountain areas, some rural areas, and so on. And also we can use RIS for some mobile backhaul of some micro base station for some offshore vessels. And also we can use to build no-cost phase array, for example, for the LEO satellite communication terminals, and so on. And as what we notice nowadays, the RIS design and the communication design are deeply integrated to accomplish the specific requirement for different applications. So I think the time is almost there. So to conclude my talk today, so we said the RIS technology and application for the 5G and 6G, we build the foundation on the surface electromagnetics, and our method is to move from conventional circuit control to the EM control. So on the surface, not only we radiate and scatter, we also do the phase changing. And with that, we can realize high gain and the flexible and the fast beam scanning. And regarding about application, we can use for the near field application. So we can use as a base station antennas, or we use it in the far field range to cover the blind areas. And as we can see here, it has several distinguished advantages. First, no cost, no power consumption, lightweight. Secondly, it can be easily scaled to high frequency, for example, to the terahertz. And it can be also affordable to build large scale arrays. And also it has good product applicability. It's very easy to be integrated into a communication system. So with that, I would like to thank very much for your attention. And also we look forward to your questions and maybe the potential collaborations. Thank you very much.
Thank you. Thank you very much, Professor Fan Yang, for this very informative talk. Actually, this is one of the hot research topics of our community. Many people are interested in starting working on RIS. Okay, so during the presentation, many attendees provided the question in the chat box. So I will read one by one, okay?
Okay.
And okay, so let me check. Okay, the first question is about the distance between the feed horn and the RIS, how it was decided and how the feed horn design was chosen.
Okay, thanks for the questions. So this is a very classical question that we do it when we design reflector array. So the distance is mainly determined by the size of the surface and the horn radiation pattern. So usually for moderate horn, feed horn, like about say 15 dB gain, the focusing is usually like 0.7 or 0.8, the F over D. That means the focus height over the diameter of the surface is usually about 0.7, 0.8. And if we have different horn of the feed, so it can be varied to 0.5 to 1. So usually it is roughly in the scale of the size of the RIS surface as well as the horn pattern.
Yes. Okay, another question. Yeah, is what's the
Same.
intelligence about the surface? It's not clear for me, but I mean, the
Uh-huh.
question is related to the intelligence
Mhm.
related to the surface and how to reconfigure the surface.
Which question?
Yeah, the second question.
Uh,
What is the intelligence behind the surface and how to reconfigure the surface?
oh, okay. Because the second question I see here is how is the feed horn design chosen?
Yeah, this is already answered. This was okay.
Okay.
Okay. Yeah.
Sorry.
Yeah,
Sorry.
we can further elaborate it.
Okay. Yeah, this one like it is more detailed. So if you are interested, you can send me email. I can reply to the second question. Okay. So yeah, it is more specific. The third question is the scanned beam should have reduced gain to the angular directivity. Let me understand the question. The scanned beam should have reduced gain to the angular directivity of the cell. I don't think so. Usually it has a increased gain because the unit cell is usually very low gain, but the surface it is a higher gain. I don't know if I answer your question or not.
Yeah, what I suggest is for those questions which are not clear, I would ask the attendant to raise the question, to raise their hand and make the question by yourself. I can unmute the microphone.
Okay.
Yeah. Okay.
Yeah, I'll follow
Okay.
you. So maybe which question do you choose?
Okay, we have several, but one is about have you performed an experiment to control wave polarization?
Yes, yes, we can do that. Yeah.
Yeah, but have you made an experiment?
Yeah, sure. So we can either like change the polarization from horizontal to vertical or from linear polarization to circular polarization. So it depends on the application requirements.
Yeah. Okay. Let me see this new code.
Oh, maybe here.
Okay, where does the quantization loss show up in the pattern scanned one?
Oh, I'm trying to follow the question. Can you repeat the question because I'm a little bit.
Where does the quantization loss show up in the pattern scanned?
Yeah, let me see if I can move back a little bit. Yeah, when we have the quantization arrow, yeah, if we can see in this slide, since we do have quantization arrow, so we see the side lobe increase. Beside the main lobe, we have side lobe increase, like for here up to more than 10 dB compared to the continuous phase. So that's we say this quantization does increase our side lobe. And furthermore, because this is a two-plane cut, if we plot the 3D plots, we see it increased the side lobe not only in the two principal plane, that is 0 or 90 degree. In other planes, the side lobe also boot up, and that degrade the performance of the surface.
Okay. Another question is about the power consumption of the control electronics. How much is the power consumption?
Okay, also very interesting question. So when we use the pin diode, the power consumption in each element is about 10 milliwatt.
I think if you compare this power consumption with some active devices, I mean, most of the power consumption related to RIS refer to this control electronics, right?
Yes, you're right.
Yeah. Okay, another question is one RIS of one operator may disturb the electromagnetic environment of the other operator. Any comments on that?
Okay, one RIS of one operator may disturb for the other operator. Okay, yeah, that's very interesting. I really enjoy this question. Yeah, this is always like a trade-off in the system level. So we have to balance between different users. And in terms of the emergency, in terms of the bandwidth requirement, I think there should be a strategy to balance this one. But I would say this will be depend more on the system management, not from our hardware point. Our hardware will provide the capability, and then how to use the capability. So we need to have some like system consideration. But that's really very interesting question. Thank you.
Okay, another question is about the typical RF efficiency of RIS. What is the typical efficiency?
Yeah, when we talk about the RF efficiency, if we talk about the element loss and things like that, usually it is for the element loss in the RF is about 1 to 2 dB, depending on the designs, depending on the frequency. Usually at no frequency like microwave, the efficiency is relatively higher. When we go to high frequency like millimeter wave or W band or terahertz, the efficiency is really low. Yeah.
Okay. Another question, is the feed an array for the near field RIS?
Yes, exactly. Yes.
Okay, another question is from one of your big fans,
Thank you.
Yeah, yeah. So the question is about applications. How do you configure the RIS in a real-time manner, especially when the terminal is under high mobility, like in the offshore communication scenario?
Yes, the answer is positive, yes. So usually from this terminal and our RIS station, so they send out their geological location, and then from that, we dynamically change the direction of the RIS so that we can always pointing the beam to the mobile terminal. Yeah.
Okay, another question, which active elements are used for the RIS design at 28 gigahertz?
Oh, good question. Nowadays, we are not using it at 28 now. So we are using at 3.5 gigahertz and some low frequency. But it can be done at high frequency. I don't think there's any big problem there.
Okay. Another question, does the simulation with equivalent RC model of pin varactodiodes give satisfactory results in the measurements?
also interesting question. So usually we have to do actually several iterative rounds. So usually the first, when we get a data, this kind of equivalent parameter from the data sheet, it usually is not the exact result at the frequency of our design. So usually we have to do some iterative. So we start with some initial design, we build a prototype, we measure it, and then from memory result, we extract the equivalent parameter, and then we do another round of design, usually through 1 to 2 rounds of this iterative, so we can find satisfactory result. So if we are lucky enough, we can get it the first time, but usually don't. So usually we take like 2 or 3 rounds, so we can get good result.
Okay, another question. Can you please explain again how you control your electromagnetic environment?
Okay, so usually what we do here, maybe I can show a, let me see. Okay, let me show an example. Like for these applications, so usually the wave propagate along this street, and then part of energy illuminated on this reflecting surface, and use that we bend the propagation of the wave part of to a vertical street. So in this way, along this vertical street, so we will have a strong signal compared to the case without the surface. So that's the idea. So we use the RIS to change the environment or to change the distribution of the electromagnetic wave in the street.
Okay, I mean, okay, it was mentioned in the chat box. The last question was, it was not talking at the RIS side node, the electromagnetic propagation side. So again, I would ask to make the question by yourself, because sometimes the question is not clear when you type in the chat box. Just make sure that it will be properly answered.
Mm-hmm. Thank you.
Okay, another question is, how do you control and demonstrate the RIS at the terahertz frequency? What kind of controlling element has been used for that purpose?
Okay, thank you. So actually that is our research right now. So we use a HAMT instead of pin diode because pin diode cannot go to that high frequency. Usually we use pin diode up to 100 gigahertz. But if we go beyond 100 gigahertz, so we are using some high electromobility transistor. So abbreviation is HEMT. So we use that one to control the on and off status of the antenna.
Okay. Okay. How was the array feed for near field RIS designed?
How was array feed? Oh, this is a similar question as before. So yeah, usually we use some like, for example, let's just show this slide right here. So this one is a RIS, and this we see design a patch array antenna. For example, it is a 2x2 microstrip patch array. And then we match the pattern of this feed with the surface. For example, we make sure when it radiates to the surface right here, the center has a strong field and the edge is about, say, -10 dB taper or -11 dB taper. So we match from the feed to the surface. So if you are more interested, you can look at some reflect array book, and they have very detailed discussion about the relationship between the feed and the surface.
What about the end feeding?
End feeding is also possible. End feeding is also possible, but it needs more complex feeding network. So if we have a power network, and this will be more complex, but it's still doable.
Okay, so still about the previous questions related to the configuration of the RIS. I mean, it was reading the chat that it was about how to configure the on-off mode of the RIS. The first slide that you provide the surface and how to configure to balance it between on-off.
Okay, so are you talking about this one, right?
Yeah.
Yes. Or next slide.
Yes.
Maybe here. So we see on and off. We use a different mode, but within this two different mode, we have a point right here. So for example, A is on the left of this minimum field zone, and in this another case, it is on the right-hand side of the minimum electric field zone. So it's a balance between these two. So we choose point A to incorporate our biasing line. Is that your question? So we look at the field distribution and the current distribution on this surface.
Yeah. Actually, there are different ways to reply a question, depends on the perspective you are So I'm not sure if it was clear answer, so the attendant could provide the further comments if it was not clear answer.
Mhm.
So another question, let me see. How to deal with a very high cost of the RIS due to the great number of active elements? I'm not sure if this is the case, but
I'm not sure about that questions.
yeah.
Even though we
Yeah.
have a large number of elements, but they are all in parallel.
Yes.
So the loss will not be added together.
In terms of the cost, if you compare with other technologies, the cost is
Uh-huh.
reduced, right?
Yes, yes. You see, we
Yeah.
don't have phase shifter.
Yeah.
We don't have
Yes.
PR module. Yeah.
Yeah. Okay. Do you have patterns for the near field RIS?
I have some like not exact that one, but it's very similar like this. Let me show. Yeah, it's similar like this. It's similar like this kind of patterns.
Okay.
Yeah, depending on the size. If we have very large
Yeah.
size, as we see in one of the example, it can be very, very sharp. So it all depends on the size and the amplitude.
Yes. Any other questions? Okay, what is the benefit over horn? Over the horn?
What is the benefit over the home?
Yeah. Yeah.
You mean the risk over the home? Yeah. Yeah, usually for home, so we only have a fixed pattern. But this one, for example, we can have the pattern that can be scanned. So I think this is a major advantage. So one, the whole antenna, the pattern is fixed. But in this one, the pattern can be changed and can be scanned.
It seems you don't have more questions. Actually, to conclude, I'd like to make a general comment. I mean, this is a very interesting research topic because if you look back 5 years ago or 10 years ago, the community, the communication, the mathematical theory of communication and the mathematical theory of electromagnetism, the community work separated. So now we need to, for a better understanding of this technology, we need to reconcile, reunite Shannon, Maxwell, Green theories for appropriately modeling, analyzing the system. So now people of different communities are working together. So this is very good because we have we get more knowledge of different fields to move forward the research. It's more challenging, of course, but it's opened the door for you starting working in another area and applying for communications. So Professor Fon Yang, thank you very much once again for your time, for this excellent talk. You are definitely one of the brilliant minds of this area with main contributions in the theory, in the practical. And we hope that we can keep in touch and try to start some joint collaborations. So thank you very much.
Thank you very much. And thanks for all the audience for your time. Thank you. Thank you. Thank you, everybody, for attending this telecom seminar. See you next week in our next seminar. Bye-bye.